All right. Uh, Good afternoon, class. Hope you're all doing well. Um, I got maybe a couple of messages that said you you couldn't see the yesterday's lesson. Um, so I'll look into that. I think I might have just forgotten to hit end stream yesterday because when I opened up my computer today, it was still on the page. So it might be up in a couple minutes or something. Um, so today, what I want to talk about is a third method of measuring the distance to stars. In this case, it's mostly the distance to galaxies, which are gravitationally bound collections of stars. Oh, one thing I wanted to show you guys. I was forging for literally 5 hours yesterday. I was forging for a long time because the weather was relatively cool. So right after I was done with my lessons, I went out and I fired up the forge, and I was trying to make myself some tongs, because I already have some tongs, but they're closed sort of like scissors, and they close like this. So they're really good at holding skinny things. If it's something skinny, then it holds really nicely. But if it's something like round, then it slips out really easily. And so I can't hold anything that's very large with the tongs. And so I was trying to make my own tong, a second pair of tongs that could hold something bigger, and it just was not working. This this took me like 3 hours to make, and it doesn't even look like anything. So I totally failed. Um, but I won't give up. Let this be a lesson to you kids. I won't give up on my tong construction. Um, all right. So, uh, hello, Kyle. Thanks for tuning in. So, what are we going to talk about today? We're going to talk about a way of measuring the distance to galaxies. And this way of measuring distance works for things that are incredibly far away. All right. So this is the way that you would determine the distance to a star if it was really, really far away. All right. So first, I want to give a little review of the Doppler effect. Okay. So the Doppler effect says that frequencies are shifted when the source and observer of the wave are in relative motion. Okay? So now what I would like to do is I would like to give you a formula for how much is the frequency shifted. And remember, frequency is basically the same thing as color. Okay? So the amount that the frequency is shifted, delta F, divided by the original frequency that is emitted, is equal to the speed of the object divided by the speed of light. And this is the Doppler effect for light. Okay. Actually, a similar equation holds if it was sound. You would just replace the speed of light with the speed of sound. Okay? So basically what it says is the larger the speed of the object, the greater the shift in frequency. Okay? Now we can, now here's a key idea. All right? Certain elements all emit certain frequencies, which are, remember, colors of light. Okay? So the frequency of the light that's emitted by a gas, for example, is like a fingerprint for what element is emitting the light. Okay? So based on the frequencies that we're seeing, the colors that we're seeing, we can tell what element it is. Okay? So you want to think about like neon signs, right? Neon signs, you get different colors by using different gases. All right? So they're not all neon. They could be xenon and other things. Or they could have additives and so on. Okay? So we can use this to measure the speed of galaxies. Okay? So what we do, now what element do you think most galaxies are made out of? What is the most prevalent element in the universe is hydrogen. Okay? So hydrogen emits certain frequencies of light, and we know those frequencies very well. Okay? So what we do is we know that the galaxy is going to emit. We know that the galaxy is going to be emitting the frequencies that correspond to hydrogen. Okay? But what we observe is that the frequency that we receive is different than the frequency that hydrogen should be. So we see that it resembles hydrogen, but it's in the wrong spot. Okay? All right? And that's because the galaxy is moving. And so what we do is we basically take this formula and we know how much the frequency was shifted because we know where the frequencies for hydrogen should be. Okay? And then we can use that to solve for the velocity of the galaxy. Okay? So we did that. We did that, and I'd like to direct your attention to the lower left-hand corner of the window here, where I have a graph where they've graphed the velocity of the galaxy versus the distance that the galaxy is away from us. So we can see that, first of all, we can see that galaxies are moving really fast because we can see that the velocity, the scale for the velocity is kilometers per second. And in fact, the middle of this graph is 5,000 kilometers per second. So we're talking about galaxies are moving real fast relative to us. And then distance, you can see that distance is measured in MPC. So what does MPC mean? That means megaparsecs, or millions of parsecs. Recall from the lesson from Monday that 1 parsec is about 3.3 light years. Okay? And so I think it's fairly obvious that there is a correlation between distance and velocity. So we can see that as the galaxy is further away, it has a greater and greater speed. Okay? And so this leads us to another key idea, is the other key idea is that the universe is expanding. Okay? The space-time fabric of the universe itself is expanding. That's what this graph says. But now, why does it say that? Why would this graph suggest that the universe is expanding? It's because if a galaxy is twice as far away, we observe that it is moving away from us twice as fast. Why does this make sense? It's because if a galaxy is twice as far away, then there's twice as much space between us and the galaxy to be expanding. If you have twice as much space expanding, you're going to have twice the speed that it's moving away from us. Okay? So space-time is expanding. Okay? The other thing I wanted to say is that all the frequencies that we observe are shifted down. Galaxies are moving away from us. So we call that redshift. Why is it called redshift? It's because lower frequency colors are redder. Okay? Now there is a significant amount of scatter in the data. This isn't a perfect perfect correlation because there's galaxies that are above the line and galaxies that are below the line. But there's a good reason for that, which is that yes, space itself is expanding, but galaxies are moving through space. So part of the expansion, or part of the velocity, is due to the expansion of space itself, and then part of the velocity is due to the motion of the galaxy through space. So you can think about, if you're on like one of those escalators at the airport. Those escalators at the airport. It's like your velocity is equal to the velocity of the escalator plus the velocity of your own motion on the escalator. Okay? So some of the galaxies are moving towards us through space, but the space is expanding so quickly that they're actually moving away from us. So you have that kind of thing happening. So this is a linear relationship, and so the Jinke asks, if a star moves fast enough, it will change color. Yes. Usually this shift is so small that it's not visible to the naked eye, but we have precise telescopes that can measure the difference. In fact, did you know that one side of the sun is a different color than the other? So the sun is spinning like this, and so one side of the sun is spinning towards Earth, and the other side is spinning away from the Earth. And so the side of the sun that is spinning towards the Earth is blue shifted. So that side of the sun is bluer. And then the other side is rotating away from the Earth, and so it's actually redder. And so we've actually used that difference in color between one side of the sun and the other to figure out how fast the sun is rotating. Okay? I think that's nifty. So at any rate, this correlation is called Hubble's law. Was discovered by Edwin Hubble, and it's a linear relationship. So it says V equals a constant times distance. The constant is called H for Hubble, and that's called the Hubble constant. And it has weird units. Its value is 68 kilometers per second per megaparsec. So again, that's really weird units. So what that means is if a galaxy is 1 megaparsec away, we could expect it to be traveling away from us at 68 kilometers per second. If a galaxy is 2 megaparsecs away, we could expect it to be traveling away at twice that, so it would be, 136 megaparsecs, or kilometers per second. If a galaxy is 3 megaparsecs away, we would expect it to be going away at 3 times 68, which is 204 kilometers per second. Okay? So here's what we do. We use the Doppler effect equation to calculate the velocity. Okay? So we know the velocity. Then we plug that into Hubble's law, and now we know velocity, so we can solve for distance. So that's how we know how far away really distant galaxies are. J&K, I just mean left side, right side, so you can see the left side and the right side. The back side of the sun is moving, left to right. Okay, so let's do an example. Hey Goldie, hey Matthew. So let's say a galaxy emits frequency of, let's say, 7.3 times 10 to the 15th hertz. Okay? Earth receives frequency 6.8 times 10 to the 15th hertz. How far away is the galaxy? And let's say that is in light years. We want to know how far away is the galaxy in light years. So, first thing we want to do is we want to figure out how fast is the galaxy moving away from us using the formula for redshift. So the change in frequency is 7.3 to 6.8. That's 0.5 times 10 to the 15th hertz. Okay? We divide that by the frequency that's emitted. The frequency that was emitted was 7.3 times 10 to the 15th hertz. And so that is equal to 0.07. And so change in frequency over frequency equals V over C. Now C is, of course, 3 times 10 to the 8th meters per second. But I'm going to write it as 3 times 10 to the 5th kilometers per second. Not meters, but kilometers. Now, why would I write it that way? I would write it that way because the Hubble constant is expressed in kilometers per second usually. So that means that the velocity on the left-hand side of this equation should also be in kilometers per second. All right? And so what this says, if we solve this equation, we get that the velocity of the galaxy is 2.1 times 10 to the 4th kilometers per second. Okay? So now we want to plug this into Hubble's law, V equals hd. So we have 2.1 times 10 to the fourth kilometers per second equals 68 kilometers per second per megaparsec times d. So notice kilometers cancel out, and we're going to have our answer in megaparsecs. Okay? All right. So, doing the division, we get d equals 308 megaparsecs. All right, which I would like to convert that into light years. So 1 megaparsec. Remember, 1 parsec is 3.3 light years. Okay, so this is 3.3 million light years. Okay, so megaparsecs cancel. And we get right around 10 to the 6th light years away. Oh, 10 to the 9th, excuse me. So this galaxy is roughly 1 billion light years away. So that's a long ways away. It's pretty cool. We can tell the distance to the galaxy. Now, actually, this is one way to sort of get an estimate for the age of the universe. As far as we know, the universe is about 14 billion years old. Okay. So if you think about it, how far could we see out? We could only see 14 billion light years away. But that actually doesn't take into account the expansion of space. So the radius of the visible universe is something like, I believe it's like 50 billion light years or something. So we could see out to 50 billion years if we had a good enough telescope. All right, so I hope you found that interesting. Oh, one thing I did want to talk about is a lot of people take the Hubble's law and they take that as appearing to show that our galaxy is the center of the universe, okay? And that is not true, okay? In fact, no matter what galaxy we live in, we would always see this same Hubble's law, okay? And here's the reason why. The entire fabric of space-time is expanding. So what if we have like a cube of galaxies, okay? And what if those galaxies then doubled the distance between them, okay? And the other dots are too low to draw. Yes, if you were in this galaxy, you would see that everything is moving away, right? So you'd say, I'm the center of the universe. Everything's moving away from me. But if you were right here, you would also see everything moving away. Because think about it. It went from this far away to this far away. So if you're in this galaxy, you still see everything moving away. So no matter which galaxy you live in, you're always going to appear to see yourself as at the center of the universe. But the universe has no center as far as we know. All right, so that's my lesson for today. I hope you have a great afternoon, and I hope you learned a little something.